So we have started by recapping on number systems, which is related to course outcome 1. So what did we see in the number systems? Even though I'm screen recording, you can still respond. This material is for you all, so don't worry. I'm not going to make it like a professional video editing kind of thing. It is just there to catch up with whatever that we are learning. So we actually saw on main position number system related to digital hardware especially. And what are the number system related? We saw decimal, binary, octal and hex, and we saw what are the allowable digits for each respective number systems. We also saw that there is what we call as the natural correspondence and compact representation, right? Octal and hex has the natural correspondence with binary, and octal and hex are the compact representation of binary. We saw that in later on examples, right? And we actually did a revision on base conversions. So we saw how do we actually convert from other base to base 10. What is the method that we use? We perform the summation of the multiplication of all the weightages of the each digit's number, right? And we saw some of the examples from base 2 to base 10 and base 8 to base 10. And very quickly we also saw how do we actually convert from base 10 to any other base number, right? So how do we do that? We perform long division with the base number. So here in this example we have 14, which is base 10, and we want to convert to base 2. So we divide by the base number that we want to convert, which is base 2. So we perform long divisions, and remember the sequence that the MSB is at the bottom. MSB stands for the most significant bit, and it goes up to the least significant bit. And then here's where the part we saw about the natural correspondence. When it comes to binary to octal and also hex, you can straight away, instead of going through the process of converting the binary to decimal and then from decimal to convert to octal or hex, we can straight away convert from binary to octal or hex. Then how do we do that? For octal, what do we do with the binary bits? We divide them into groups of 3. And what do we do with if hex? Divide in the group of 4, and vice versa. Each digit in hex is equally represented by 4 binary bit, and the same thing goes with octal. Each octal digit is represented by 3 binary bits, and that is what is known as the natural correspondence. And then very quickly we saw, just to recap on binary addition and binary subtraction, this is quite straightforward and simple. And we ended with STP questions. What is STP? Something to ponder. And what are the two questions that we have? What is 2's complement number system? And second, why do we need to use 2's complement number system in digital hardware? So did you all find the answer? Okay, so why do we actually need 2's complement number? What is the answer? You all can talk to me. So why do we need? The reason is we want to express positive and negative numbers within a fixed length number. So what do we mean by fixed length number? So whenever we deal with digital hardware, so the digital hardware, because it is a hardware, let's say, remember in the first class I've actually showed you the PIC18 microcontroller. I think some of you missed it, but in our first class I did show you the actual hardware that we were actually learning, or will be learning throughout this whole semester. Now that particular microcontroller is known as 8-bit microcontroller. Whenever we say it's an 8-bit microcontroller, it means that it can process a data length of 8-bit. Does it make sense? Another question, how many bit is your computer, your laptop? 64 bit architecture, right? So when you say 64, what does it mean? It can process a data length of 64 bit at a time. and the previous one was 32-bit. So but microcontroller, it's on a lower end, so it's 8-bit. So whenever we say 8-bit, so the digital hardware allows 8-bit to be processed. So that is a fixed length data type, right? That's a fixed length. The digital hardware, you can't change it. It's not on software, it's hardware. It allows 8-bit data to be processed at a single time. Now of course, what happens if you want to deal with more than 8 bits? Of course, that is possible. That always can be done. So that we will be seeing later. But when we say it's an 8-bit microcontroller, that means the data length will be 8-bit. Now that is a fixed length, right? So within that fixed length, if you want your microcontroller to perform some arithmetic operation using real numbers. Now when we say real numbers consist of positive values and negative values. Are you following? Don't worry much about writing these notes. As I told in the previous class, I did share with you the notes, right? So coming back to the point, so it has fixed. So to cater for both positive and negative numbers within that fixed length, we need to use 2's complement number. Are you all following? So now sometimes whenever we write, say we write something as -8. This is we are writing. Are you able to see the screen? We write -8. So how do we know this is a negative number? By looking at the negative symbol. So this is in terms of visual. You're writing something. Or if you just put +8 or just leave it as 8, you know the number is positive, right? But when it comes to digital hardware, and when we want to perform arithmetic operation, we have to deal with both positive and negative numbers. So therefore, the one way that we can actually express positive and negative number is by using 2's complement number system. Is that okay? Now the next question comes, how? So when we say we have a fixed length of 8-bit, so we have 1, 2, 3, 4, 5, 6, 7, 8. 8-bit numbers. So how do we represent positive or negative number? The answer is there also. By using most significant bit as the sign. Remember earlier I have actually wrote -8 and then I wrote +8. The negative and positive, that sign now is expressed through the most significant bit. Are you all able to follow? So we have 8 bits here. Where is the least significant bit? This one. This is the most least significant bit, and this is the most significant bit, and the bit position is 0, 1, 2, 3, 4, 5, 6, 7. Total of 8 bits. So the 8th bit, or bit number 7, or the 8th bit, is used to express the sign. So how do we express? Because binary has how many possible combinations? 2, 0 or 1. So it is just nice to express 2 signs. So when you write 0, you are expressing it as a positive number. When you write 1, you are expressing it as negative number. So that is the sign. Any question up to this point? Able to follow? Okay, okay. Oh. So, for example, you have 0, 1, 1, 0, 1, 1, 1, 1. How do you know whether is this a positive or negative number? Okay, fine. Now, before we look at the most significant bit, there is one important term that we need to look upon. Signed and unsigned. There are these two terms, signed and unsigned. Because this is a normal binary number, right? Now if you are required to convert this into equivalent decimal value, and the question says that this is an unsigned binary number. Please convert this unsigned binary number. So what it means by unsigned is there is no sign convention, which means you don't treat the most significant bit as a signed value. You treat it as any other value of in the binary bit. But if the question says convert the following signed number to equivalent decimal, then you have to look at the MSB, most significant bit. Is that okay? So that is these two terms that you need to be aware of, unsigned and unsigned. So whenever we say signed, signed is actually referring to 2's complement number system. 2's complement number systems are signed numbers, which means they are either positive or negative. Unsigned means the number doesn't have a positive or negative value. Is that okay? Shall we move on? We will do some examples, then you can get a better grip of it. Now, the 2's complement number system, which I am using abbreviation CNS, can represent integers in the range. Now, if you have 8-bit value, 8 bits, right? Let us stick to 8-bit. Why we are using 8-bit is because our microcontroller is 8-bit. So let's say if a normal binary bit is an 8-bit binary, what is the value that it can represent? The range of 8-bit number. What is the minimum value that it can represent? No, unsigned, normal binary number. The minimum 0. Unsigned, it is 0. So unsigned means you are 0 0 0 0 0 0 0 0, and then each bit keeps increasing until the maximum is 1 1 1 1 1 1 1 1. Now assuming that this is unsigned, so how do you find the range? This is the minimum, which means you get 0, and this is the maximum. So how do you find this value? This is 2 by the power of 8 minus 1, right? This is, you have seen this formula before, 2 by the power of n. N is referring to the number of bits. Do you remember, or have you all forgotten? Forgotten. Okay, forgotten, never mind. I'll just rewrite it back in a proper format. N. 2 by the power of n minus 1, whereby n is the number of bits. Is that okay? Okay, something happened. No. Are you able to follow? Are you able to see that clearly? So which means the answer is you get 2 by the power of 8 minus 1. What is 2 by the power of 8? 256 minus 1? 255. So the maximum range is 255. Why do we minus 1? Yes, because we're starting from 0, so you need to minus 1. So if the number is unsigned, the range of unsigned 8-bit number is from 0 to 255. This is unsigned. Now what if it's signed? Now when it is signed, the range of number changes, because the range will also represent negative numbers, right? And therefore you can follow this particular formula. If you miss something that you want to write, just let me know, then I'll just shift back the page. The best part of using tablet is I can enlarge my fonts as how I wish it to be, so that's nice. So you use this formula. Remember this formula. This will be very important. So whenever it mentions 2's complement number system, you need to follow this formula. How the formula goes is negative 2 n minus 1, that is the negative range, and the positive range is 2 n minus 1 minus 1. Is that okay? Can I ask you a simple question? Why do we do n minus 1 here? Why do we do n minus 1 for 2's complement number system? Yes? Try to answer something. Why do we do n minus 1? Yes? What's that? Try. Because we have a negative number. Okay, coming close. Yes, something related to that. Why do we minus 1? We have seen the answer just now actually. Why is the total number of bits is being minus by 1? Because? Yes, because the 8 bit we are using as a sign, right? So you cannot take into account to count its value. It's used as a sign. So we need to n minus 1. Simple, right? Simple or no? So when you understand, things becomes much more easier. So that's why we do n minus 1. Why do we minus 1 here? In the positive range, why do we minus 1? Yes, because including 0. So let's see the example. Find the range of integer that can be represented by an 8-bit 2's complement number system. So this is signed number. So you have to use which formula? You have to use this formula. So negative 2, n is 8 minus 1 is 7, and you get 2 to the power of 7 minus 1. So what is negative 2 to the power of 7? 1 to 8. The range is, this is 1 to 8 minus 1, 1 to 7. So this is your answer. So what it means that with an 8-bit number, you can only represent a value of negative 1 to 8 until positive 1 to 7. Can you represent negative 250 using 8-bit? No, you can't. So that is the limitation. So with 8 bits, these are the range of number that you can deal. Very important for you to understand that. Is it okay? What if the same question asks, find the range of integer that can be represented by an 8-bit unsigned binary number? What would be the answer? 0 to 255. Everyone managed to understand? Is the darkness making you feel asleep? Are you here with me? I'm sitting in one place and doing this thing because I'm connected and trying to write. Any question up to this point? Can we move on to the next one? So the next thing that we want to try to recollect is on 2's complement number systems, negation, addition and subtraction. So let us see the first one, which is on 2's complement number system, negation. So what is negation? Negation is simple. From the term itself is to negate a number, to negatify a number. That's what it means. If you negate a negative number, what you will get? Positive. If you negate a positive number, you get negative. So negation. Are you all following? Because you are all very quiet. I don't know whether you understand or not. So what are the steps for us to actually negate a number in 2's complement number system? Is they have these 2 steps. The first step is to invert all bits, which is also known as performing first complement, and then the second step is you add 1. So basically what you're doing, this is performing 2's complement. So when the question says perform 2's complement on the number, means you perform negation. So negation is another term to perform 2's complement. So let's say you have this example here, negate 00110101. Now because this term's negation only happens in signed number. So is this a positive or negative number? How do we know that this is positive? So the most significant bit is 0. So thereby it is represented, it is a positive number. So when we do negation, you're supposed to get negative number. So let us see. So what are the steps for negation? You perform first complement, which is you complement, invert all the numbers, and then what you do, you add 1. So you get 1 1 0 1 0 0 1 1. Now look at the most significant bit now. What happens? It has become negative. Is that okay? Any question up to this point? Okay. Now let us go to the next part where we want to perform 2's complement number system addition. Now what is the difference? Earlier we also did addition, right? Binary addition and also binary subtraction. Now in 2's complement we also have addition and subtraction. But what is the difference? Can anyone try to guess? That is unsigned, this is signed. So which means you are dealing with signed numbers. Is that okay? Now we have this one example, 63 plus with 27. So can we perform addition? Now you may think that, wow, it's so easy. Just put like this, 63 plus 27 get 10. This is 8, 90, done sir. Then what I'll be doing? Wrong, 0. Do you know why? Is the answer wrong? Huh? Why do you think you'll get 0? What, come again? What the question asked? I did what? 63 plus 20. Yes. It says perform 2's complement number system addition. Remember this. 2's complement number system are always represented in binary. So don't get excited. So easy. This one standard for question. Can do. I get a big 0 there. So what you have to do now? We have to convert this into equivalent binary, right? Now here is where, remember we recapped earlier all about all this conversion. Now does it come in handy? So now we have base 10, we need to convert to base 2. What is the technique that we should use? Long division. But I don't like long division. So we're going to use an easier way of doing this. So what is the easier way is, remember we are always dealing with 8-bit. So each one of this bit has its own weightages, right? 2 by the power of 0, 2 by the power of 1, 2 by the power of 2. So write down those weightages. So we'll write as 1, 2, 4, 8, 16, 32, 64 and 1, 2, 8. Do you all know how I got these weightages? This is 2 by the power of 0, 2 by the power of 1 until 2 by the power of 7. Got it? So write down the weightages like this, and then what you do is you need to convert this 63, right? So 63, out of all these weightages, which weightage is less than 63? 32. So you put a 1 here. Take away 32 from 63. What is the remaining? What is the remainder? 31. You get 31. How can you represent 31 using these weightages? 16 plus 8, 24 plus 4, 28 plus 2 plus 1, 31. So 1, 1, 1, 1, 1. So you manage to solve it. I call this the plugins method. Just kidding. Or another way that you can look at this, I am not so sure if some of you have captured this or not, but it's quite easy. That's what is another way. This is 63. Do you see there's a weightage 64? It means that this is one step below 64, right? So what is one step before 64? 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. 63. If you add 1, then you will get 0, 1, 0, 0, 0, 0, 0, which is 64, right? Are you all following? So that's one way of looking at it. So we add, then we do for 27. Which one of this weightage is closest and less than 27? 16, right? So take away 16 from 27. Can't be that bad, right? Your maths. 11. How can you represent 11? 8, 2, 1. Done. So I believe this is much more faster than the long division. Of course, you may argue, sir, calculator is faster than you. Well, that is correct. Calculator is faster. But you will sunk out at one point whenever you are doing the negative numbers. That they have some issue. So once you have convert this, so you can see that both numbers are positive. So now when you have represented this number into equivalent 2's complement number system, now you can perform the addition like normal binary addition. So help me out here. So 1 plus 1, 2. So you get 3. This is 2. This is 3. This is 3. This is 2. 0. What happened? Oh, nothing's coming there. Okay, so we have resumed back. So this is the answer that we have got. Any question up to this point? So we are going to continue with another example. So we have another example here, 97 plus with negative 13. So here we have something different. So again the same method is what? We write down the weightages. So I'm going to write the weightages in reverse now. 16, 8, 4, 2, 1. So memorize these weightages. It will be easier for you to do. So let's do the first digit, which is 97. Which one of these weightages is closest to 97, less than 97? 64. So write 1 here. So take away 64 from 97. 30. 33. How can you represent 33? 32 and 1. So it's fast, right? So the remainder you can all put 0. Now you want to add with negative 13. So here we got a bit stuck. So how can we represent negative 13 based on the knowledge that you have acquired so far? Write the normal positive 13 and then apply the 2's complement, you'll get negative 13. But I don't like that technique also. Yeah, you can use that, but there is a shorter way of doing that, which I'll be teaching now. Is in essence is actually nothing but the same thing, but just changing something. So you have negative 13 here. Just take the value 13 and minus 1. What do you get? 12. Good. How can you represent 12? 8 and 4. Now when you represent 8 and 4, you represent using zeros instead of 1. Earlier we tried to represent by using ones, right? For negative number we just represent using zeros. Done. So rest all 1. So you don't believe? Let's try to write it in normal 13. So normal 13 is 0 0 0 1 1 0 1, right? This is normal 13, positive 13. And if you perform the negation, how do you do negation? You perform, then you plus 1. Do you get the same answer? This is the Prajin's method. Just kidding. So just to recap, for positive number you look at the weightages of the ones, right? For negative number you take the value of the negative number, which is like negative 13. You just take the value, which is 13, and you minus 1, so you get 12. So what do you do for negative number? You try to represent 12 by using zeros, and then the remaining you just fill it up with 1, and automatically you get the value of negative 13. Is that okay? So after you have done this, now you perform addition like normal. So 1 plus 1, 2, you get 2, you get 1 0 1, you get 2, this 3 2, you have a carry 1. So I'm going to just use a bracket to differentiate the carry from the 8-bit value answer. Any question up to this point? Again, don't worry about writing, worry about understanding. Are you able to understand? Sure. Anything which is unclear? Shall we move to the next example? So the next example is still using 2's complement number system, but now we're going to perform subtraction. So the same principle applies. Now take note that here these two values 15 and 8 both are positive. The operation that we want to perform is subtraction, which is negative. So again the same thing, we write down the weightages. What are the weightages? 1 to 8, 64, 32, 16. What happened to the remaining 4? 8, 4, 2, 1. Easy, right? It's okay. So how you want to represent 15? This is easy. This is positive 15, right? So you're going to perform minus 8 is of course 1 0 0 0. So you have this. So this subtraction is easy. 1 1 1 0 0 0 0 0. So this is the answer. It's quite straightforward, right? Any question up to this point? So I'll just stop the video here.